Okay, so I think we can start. Before the break, we were talking about surrogate models, and till date we have talked about what? Two types of surrogate models. One was the response surface method, which is basically polynomial regression. The other one is the PCE or polynomial chaos expansion. And in PCE, there are two types. One is the intrusive polynomial chaos expansion, where you use the governing physics, Galerkin projection, collocation to come up with coupled equations which you solve using some numerical technique. The other one is the non-intrusive polynomial chaos expansion, which is linear regression model only, but your basis is the basis function you use are the orthonormal or orthogonal basis. And that is what we have discussed till now. So this is kind of, we are midway through our discussion on surrogate model. I am going to discuss one more surrogate model, actually two more maybe. So Gaussian process I am going to discuss starting today. And then we will talk about high dimensional model representation or ANOVA decomposition. And with that, we will kind of wrap up our discussion on surrogate models. Okay, we will wrap up our discussion on surrogate models. Okay, and that will also wrap up our discussion on what? Module 3, I think it is. Or module 4, if I take the basics as one module. So that will, with that we will complete module 4 and then proceed to system reliability, time dependent reliability, and so on and so forth, right? Okay, so with that background, we are going to talk about Gaussian process, but if you look at the slide, I am also using the name Kriging. So Kriging and Gaussian process are kind of synonyms. Gaussian process, I will use the term Gaussian process primarily, but in the reliability literature at least, the Kriging name is more popular. The name Kriging came from the scientist or engineer, not scientist actually, Krieg, who was a South African scientist who first used this for geospatial data in long back in 1951 or something like that. And since then this name Kriging came to light. But essentially Kriging is nothing but Gaussian process. It is basically Gaussian process. Okay. Okay. But before we go into Gaussian process, we need to discuss certain aspects of probability and statistics. Now in probability and statistics, we did a review at the beginning. And there we talked about random variable, right? Now mathematically, if I have a random variable x, it is denoted as x omega, okay? So suppose x is a random variable, then we will denote x as x omega, okay? So this is denoted as x omega, where omega belongs to capital Omega. Now what is this small omega? What is this capital X? Let us spend 1 or 2 minutes trying to understand that. X, I already told you, is a random variable. Let's assume X to be some arbitrary Gaussian with mean mu and standard deviation sigma. Small omega in that case you can assume to be standard Gaussian, zero mean and unit variance. So that means capital X is a function of small omega. So basically X is random variable, and that random variable is function of some primary random variables, which in this case is omega. So, and this omega comes from the probability space, which is capital omega. So capital omega is the probability space. So from that space you have omega, which are some set of random variables, let's say standard Gaussian. And now your random variable is function of that standard Gaussian, so you write it as x omega. Now when I am saying standard Gaussian, that's just an example I am giving, it need not be standard Gaussian, but it is some random variable from the probability space. Okay, so this is just for representation's sake and this is needed for the discussion today, so I am bringing it up. Until now we did not discuss it because we did not require it. There is no requirement for this omega kind of representation, but we will need it today, and that's why I am bringing it up. Okay, so a random variable is denoted as x omega, where omega is some random variable from the probability space. So in this probability space, those are like points. Okay.
In the probability space, all kinds of distributions exist, and
Yes. Yes.
standard function.
Yes, I mean the probability space is a probability space where you have probability measures, right? So if you kind of restrict it, you can assume that all type of Gaussian exists there. If you make it more generic, everything exists there. So all of those you can think, and from there omega is like a random variable, right? And your x, which is the actual random variable, is function of that omega. So omega represents randomness. The fact that there is a omega, you should understand that means x is random. If omega was not there, then x will be a scalar or a vector, but it will not be a random variable. So omega being there represents that x is random. So that's a representational thing. It has nothing to do with actual thing, but it's more of a representation thing. Okay. Okay. Now, if this is a random variable, what I am going to discuss or start discussing today is Gaussian process. One example of random variable is Gaussian distribution, right? We are going to discuss today about Gaussian process. So if I link it to random variable, there should be something known as the random process. So what is a random process, right? So what is random process? Okay. Now for random process, there is a formal definition and there is a definition that I will tell you, which is not formal, which you should not tell anyone if they ask you. Let's say if I ask you in exam, you should not write that, but that will actually make things clearer, that will give you a better intuition. So the formal definition is a random process is a collection of random variables. That's a formal process. A Gaussian process is a collection of random variables, any finite set of which follows Gaussian distribution. That's a formal definition of Gaussian process and random process. What is a Gaussian process? A finite collection of random variables, a collection of random variables, any finite number of which follows a consistent Gaussian distribution. That's a Gaussian process. Now this will not make sense, that's fine. It will make sense in a short while. A random process, it will no longer be Gaussian, but it is a collection of random variables. Okay. What does it mean? We'll come to that. Okay. Not today, maybe tomorrow, in the next lecture, but I'll come to the intuition at least today. Okay. So it's a finite collection of random variable. Okay. Finite collection, or maybe I should not say finite, it need not be finite, collection of random variables. Okay. Now, okay, I understand, till now it is not making sense, so let us try to make sense out of it. Okay. How do we represent a random process? A random process is represented as, it is represented as x and I am assuming t, time, okay, slash omega. This is how you are going to represent random process. X, and x is a function of t, which is time, and also function of omega. And the fact that it is function of omega denotes that it is random. If omega was not there, it's a normal time series, a deterministic time series. The fact that omega is there, it's a random time series or a random process. Okay. So now, from this, when I said it is a finite collection of random variable, what do I mean? Let us try to understand. So this t is time. Practically, you will measure this x at some finite times. Let's say I measure this x at t1, t2, t3. So what will I get? x1, x2, x3. Correct? What is x1 a function of? Omega. That is a random variable because it is only function of omega. T I have fixed. What is x2 function of? Omega. It is not a function of t because it is at t equal to t2. What is x3? Right? And like that I can sample at infinite number of t's. So I can get infinite collection of random variables. So a random process is a collection of random variables. So basically it is we are calling it collection because you are sampling t at different point and you can sample t at whatever point you want. Whenever you sample at t, you get a random variable. All those collections together is what represent xt semicolon omega. So you start calling it a random process. Yes.
So it is like always when we are talking with time, then we will say that random process.
I'll come to that. For now, the original definition is with respect to time, but we'll come to that. Okay. The original definition of process.
In random field also we have this thing.
That's a field. So that's why I'm coming to that. I'll come to that later. Okay. So for now, you don't need to go there. The original definition of process was based on time. Okay. Anyways, let's come back to the definition. Is the definition understandable now? So it's basically we are calling it a collection of random variables, not a finite collection because it's actually an infinite collection. Because you can sample t as many times as you want, and for each sample of t, you will get a random variable. And those random variables for all t, that collection is basically denoting xt semicolon omega. That's your random process. So that's how the definition in potentially infinite collection of random variables comes into picture. Okay. Now if it was a Gaussian process, okay, then this x1, x2, x3, x4, no matter whatever you sample, this will always be jointly a Gaussian distribution. So when you talk about Gaussian process, so this x1, x2 that you are getting by sampling t, those will always be a consistent Gaussian distribution. When I say consistent, that means the mean will form a pattern, the covariance will form a pattern. And that will become Gaussian process, which is a random process. Okay.
So each individual x that we get, would that be a Gaussian variable or
That will also, that's a property of Gaussian. Marginal distribution of a Gaussian is Gaussian. That's a property. So if the joint is Gaussian, marginal will also be Gaussian, conditional will also be Gaussian. Everything is Gaussian. Okay. That need not be true for other distribution, by the way. But for Gaussian process, that holds. The definition says that jointly Gaussian, but because jointly Gaussian, everything is Gaussian from the definition and properties of Gaussian. Okay. So now coming back to what he was asking, that is random process always a function of time? No, not necessarily. This t can be replaced by any deterministic variable. It will still be a random process. For example, space. This x can be function of space and still be random. Now, generally we use x for space, but let's say z for, no, not z. What should I use? X tilde. Let's call x tilde for space. So, another way of representing it is that x, let's say it is function of some deterministic deterministic variables, which changes, by the way. Variable means it changes. Let's call it, suppose it is space. So space is small x tilde semicolon omega. So the original random process was changing with time and was random. Now this one is changing with space and it is random. This is also a random process. This is also a random process, but normally in literature it is called random field. And the name makes sense because field, naturally in our mind we relate it with space, process naturally we relate it with time. But if you say both of these are process, you are correct. You are not wrong when you are saying both of these are process. But random field, the name became more popular because naturally when I listen to the term random field, I understand that it is random and it has spatial variation. When I hear this term random process, I understand it is random and it has temporal variation. So that is for our own intuition, but both of these are actually random process. The name random field came much later. Random process was the original name that came. Clear what is a random process? The definition is clear. How is it coming? Now in the random field case, you will sample x, and for each of those x you will get a random variable, and collection of those random variable is your random process. Same idea. Exact same thing. Okay. Okay, and by the way, when I am talking about space, this x tilde is a vector. It can be x1, x2, x3. I mean x, y, z, 3D, right? 3D space. So it need not be one dimensional. It can be 3-dimensional also. So naturally, in that case, space might become more complex than time. Which distribution? Yeah, that's a property of Gaussian. That if x and y are jointly Gaussian, then x is Gaussian and y is Gaussian. Not only that, x given y is Gaussian, y given x is Gaussian. These are all properties of Gaussian distribution. If x and y are jointly Gaussian, no matter what you do, x and y will always be Gaussian. You cannot change that fact. That is mathematically proven. That cannot be changed. No matter how you are arriving at that joint distribution, does not matter. If x and y are jointly Gaussian, then x is Gaussian, which is a marginal distribution. Y is a Gaussian, which is a marginal distribution. X given y is Gaussian, which is a conditional distribution. Y given x is also Gaussian. And not only that, you can find the properties exactly, the mean and standard deviations. And because this holds, that's why the Gaussian process regression exists. Because the Gaussian process regression is all about marginal and conditional. We will not see that today, at least the mathematics we will not see today. But next lecture you will realize when I go into the mathematical part that everything is about this Gaussian distribution property, and that is the reason this Gaussian process exists. Without those properties, the Gaussian process will cease to exist. No one will use it. Okay. So it does not matter. Okay. If A and B are jointly Gaussian, A is Gaussian, B is Gaussian, A given B is Gaussian, and B given A is Gaussian. Okay. Any other question? So definition is kind of okay, right? Now I said I will give you another intuition based definition, right? The intuition based definition is that in the real world you will not be able to sample x at infinite number of t's. You will sample x at some finite t, right? So when you sample x at some finite t, what will you get? You will get a random vector, correct? If you sample at 1t, you will get a random variable. At 2t, 2d vector, random vector. 3t, 3d random vector, and you keep on increasing and you will get random vectors. When will the vector become function? When this number of vector elements tends towards infinite, right? So in that sense, you can imagine that Gaussian process or a random process is nothing but generalization of random variable to infinite dimensional vector. Because you are now increasing it 1, 2, 3, n, and that n goes to infinite. When it goes to infinite, then only it is infinite collection of random variables. And that is the time you start calling it a random process. So that means it's a process, random process is nothing but the infinite dimensional random vector. Obviously, you cannot work with infinite dimensional, we'll have to work with finite, but intuitively you can relate it to that. So now, if this is clear, let us try to understand it a little bit more. The same thing, forget about the random part. An infinite dimensional vector can be thought of as a function. Think of a function. A function you can sample at sin x. You can get sin x at infinite number of x's. When you sample it at 10x, you get a 10-dimensional vector. When you can actually sample that x at infinite number, then you actually get the sin x function. So a function, you can think of it as a vector which has infinite elements. Right? So that means a random process is a distribution over function. Because that's what you are doing. If I remove this omega, what is it? X of t. It's a function. Because omega is there, it is making that function random. So it's a distribution over function. A random process is a distribution over function. That function can be 1D, time. That function can be 2D, function of space. 2D space can be 3D, function of 3D space, can be 4D, 3D space and time. It can function of all four. And it can be n-dimensional also. In that case, it will not be space and time, but you can imagine it as some input variable. Some input variable. Some input variables which are not space and time, but some generalized input variables. So the take home message for you that will I think will stay with you is that think of random process as a distribution over function. Random vector is a distribution over vector. Random variable, the scalar one, is a distribution over a scalar variable. So that is how you can relate these three entities. They are not different. I mean, they are different, but at the same time, they have many similarities. Okay? But this is intuition. The actual definition is what I have written. Any question?
So, just like we were sampling from a random distribution for a variable. If we want to sample a value for a function, then we can use a random process.
Exactly. So, and that is the next very important point. So, if there is a random variable, you sample it. If it is a random vector, you get vectors. If it is a random variable, you get values. If it is a random process, each sample will be a function. So, Gaussian process, when you sample, you get a function. Okay. So, you are right, exactly. When you sample a random process, you get a function.
So, for random process, we always consider finite, that won't be a random process.
Okay. Sin x ideally is infinite, but for practical purpose, when you write a computer code, we only evaluate it at certain points. So that is what we will do. So technically it is infinite, but we cannot work with infinite domain, we will work with finite domain. But technically it is infinite, or it is a function. It's either an infinite dimensional vector or a function, obviously. Right? Okay. Okay. So how will you, now I also want you to take with you a visualization of random process. So if I have to draw a visualization of random process, it will potentially look something like this. So there will be three axes. Okay. And I am going to go with time because I have used x, so it will be easier. So this is my time axis. Okay. This is my omega axis. And this is my x axis. Okay. So suppose I draw a okay, forget about that. So now If I draw a sample from this x t comma omega, how will it look like? A sample from x t semicolon omega. How do you think it will look like? One sample. T is 1, by the way. No. X t semicolon omega, that is the random variable. I am drawing one sample from there. So first thing you need to realize is that from a random variable, when you draw a sample, that is actually deterministic. The sample is not random, the variable is random. Dice throwing is a random experiment. Once you throw it, you get a sample either head or tail. Either 1 or 2 or 3 or 4 or 5 or 6. So what you get is a sample, and that is deterministic. The outcome of a random experiment is deterministic. But that experiment will change every time you perform the experiment. That's why you call it random. So when I perform the experiment once, I get a sample. How will that sample look like? It will be some function of time. As I said, when you draw a sample from a random process, you get a function. So it will be some function. Function of what? Time, because x t semicolon omega. So it will be something, let's say something like this. Some function, right? And let's say this corresponds to omega equal to omega 1, which means some value of omega. So that means one sample. If I draw a second sample, how will it look like? Some another, this kind of behavior, some other behavior, but the second sample will potentially, I'm just drawing it, but it may potentially look something like, I don't know, right? Something like this, right? And if I keep on drawing samples, I will go in this omega direction. And in omega direction, the omega axis, each point is representing a realization. Because the omega axis is the random axis, which you will generally say ZA, I think, if I x, y, z, if I say, but omega, the one that is coming out of the board, that is the random axis. So each point on that represents a random sample. And I can keep on drawing, right? I can draw a third one also, which might be something like this, right? Clear? So each of this different color is representing a random sample, which is a function. Correct? It's a random sample, which is a function. Let us go one step ahead. So now let's take this point. Let's call it T1. So at T1, this is my value, this is my value, this is my value. So if I take these values, and this I might have infinite number of samples, you can imagine. What is this? I'm not talking, it is not Gaussian process. So what is this? These are samples x1 omega. This represents x1 omega. This is a random variable. This is the random variable x1. Remember I said that a random process is a collection of random variables. So this is one of such random variable along with all the realizations. So this is your x1 actually, and it's a function of omega because it is random. Whereas this one is x at x1 of t, let's call it. This is x2 of t, this is x3 of t. 1 at the superscript means sample. Some random function you are getting, second random function, third sample, first sample, second sample. Right? And when I say x1, 1 at this subscript, it means random variable or random variable at time t1. Similarly, I will get a random variable at time t2 if I draw it, right? And I can get infinite such collection of random variables, x1 omega, x2 omega, and so on and so forth, right? So visually, when you think about, by the way, the vertical axis gives you the magnitude. That's simple, right? So this representation that you see now on the board or on the screen, this is a visual representation of a random process. So when you think of random process, this is the mental picture that you should develop for random process. That it's something that is function of time and randomness, which is omega. Each sample is a function that changes with time. Now, if I fix time, I will get random variables and all samples of random variables. And this one is the magnitude. So, this is the mental picture that you should develop when you hear the term random process. Okay. So, before going further, let us try to summarize what we have discussed till now. Okay. Random process, first of all, we defined it as collection of random variables. Okay. We also said that it is basically a distribution over function. And because it is a distribution over function, each sample from it is a function. Right? And now with that in mind, this is the mental picture that you should have, where each sample is like a function. And if you fix a point time, then you get a random variable along with samples of random variable rather.
So that will be a distribution.
Which one?
That x at given time, whatever all the samples we will get.
Yes. So x1 omega is a random variable. Naturally, a random variable will have a distribution. But I have not drawn the distribution here. Here you will only get the magnitude of those random variables. Now you can fit a histogram, normalize it. That will be your distribution.
We need to normalize it.
Obviously, you can draw a histogram and then the area under the curve should be equal to 1. So, because of that, you should normalize it and that will be representative of the PDF. So, that obviously you can do, but what you are getting here, these points, this is not your PDF. This is your variable values, a sample of x1 rather, I should say. Okay, these are the samples of x1 you are getting in the y-axis or in this case x-axis. Okay, any question on this? Because this is the fundamental part. Obviously, random process, random vibration, there are courses on that. Random vibration is a semester long course that can run. Random process definition, stochastic process is like it can be a total semester. If I go about defining all the properties of stochastic process and all those things, it's a semester. What I want you to take away is basically an intuitive understanding of what a random process is, so that when you go to Gaussian process, you are able to appreciate that. So, is that clear? I mean, from that point of view. Obviously, I am not expecting you will know all the properties of random process. I am not expecting that you will be able to derive all the properties of random process. That is not the expectation. Yes, you should be able to derive the properties of Gaussian process, but by the time I complete it, not now. So, expect some derivations on Gaussian process in the homework, for example. Okay, but nothing on random process as such. Okay, clear? So, if this is clear, we are talking about surrogate model, which means you can imagine it as a regression, some kind of, correct? So, when I am saying Gaussian process or Kriging, the idea is that we want to use Gaussian process as for regression. We want to use Gaussian process to build a surrogate. Now, whatever I have discussed till now, there is not even a clue about how it can be used for a surrogate model, for building a surrogate model, right? It is some distribution over function, that's all you know. But you do not know how it can be used for building a surrogate model, right? And that is the main focus. This was just the introduction to random process. So, now let us go to how it arrives and how it results in a function and all of those things, okay? How you can actually use it to train a surrogate model will come in the next lecture. But at least some schematic understanding, some schematic representation of this Gaussian process, which will give you an intuition that how it can potentially be used for regression or surrogate modeling. Okay. Okay. The title is wrong. it should be GP for UQ. So clearly, okay. I took the figure from my previous slide, but I forgot to change the slide title, as you can see. Okay. Think of a surrogate modeling problem or a regression problem. What are you generally trying to do? You have observation X and Y pair at certain points. You want to build a model which you can use to predict at new points. That's what you want to do. Reliability analysis, you have 100 samples. You want to build a surrogate model so that you can use the surrogate model to evaluate at 1,000,000 points very quickly and use those 1,000,000 samples to do MCS to find a reliability. That's what you are trying to do, right, in this course. So if that is what you are trying to do, if we only talk about the first part, which is building the surrogate model and making prediction, not go to the million and do reliability, but only up to building a surrogate model and making a prediction. It is a regression model, right? And in a regression model, this is what you are looking at. The red dots are the points where you have measurement. And those might noisy, you can assume them to be noisy, okay? And what you will want is you will probably try to predict at, let's say, at 6. You have measurement at what? 1, 1.5, 2, 10, 16. X-axis, at those points you have measurements, right? And you potentially want to predict at 6 or 7, some number, right? That's what you want to do, right? So what you will like to do is, you will like to get something like this. You fundamentally want something like this, right? You want to learn a function, which is the blue line that you see. But you will also want to learn the uncertainty. And now I am bringing a different types of uncertainty into the picture. The uncertainty in your model. Because whatever model you are learning is only an approximation. PCE is not exact. Response surface method is not exact. Neural network cannot be exact. None of the machine learning model can be exact. So because they are not exact, there is some modeling uncertainty, some additional uncertainty that is there in the picture as well. Until now, we were ignoring that. We were only considering the uncertainty in the x direction, in the x axis. That my input variable x is random. But what about the uncertainty in the model? That because the model is imperfect. That is a type of epistemic uncertainty. This is the epistemic uncertainty because you are learning from limited amount of data. And you can understand that because look at the plot. This band is uncertainty. Where is the band reducing? Wherever the point is there. Where is the band increasing? Wherever the point is not there. So if you have infinite number of points, what will happen to the band? 0, which means what is this uncertainty telling you about? Limited data uncertainty. Obviously, there is one more type of uncertainty, which is the uncertainty in your noise, because of noise in the data. So ideally, if you have infinite data, the uncertainty is only uncertainty because of the noise in the data. But if that noise is 0, then uncertainty is equal to 0. So this uncertainty we are ignoring till now. Now we are also bringing that into picture. And it will come into picture because Gaussian process is what? Distribution over function. So what do you think this is representing? You draw multiple functions and then from there find the upper bound, lower bound and plot them. You will get something like this, right? So this is what we want to do. This is not what we know how to do. We do not know how to do it, but this is what we want to do. And hopefully by the end of next lecture or the lecture after that, by the end of this week, let's say, you will be in a position where you will know how to do this. Where you will know how to build a Gaussian process that will give you a mean prediction, which is the blue, deep, dark blue line, along with the uncertainties. And you can verify your code because the uncertainty should increase when you are away from a point and it should reduce as you approach a point. And at that point, it should be 0, assuming no noise. So that is a verification you can do. So this is what we want. Okay, but we'll not do it today.
So when we do predictions from a point, if we have the same hyperparameters, then even after doing multiple times, we get the same value.
Not true. Not true. What you have learned here, you will learn a Gaussian process, right? Let's say I am predicting at 6. What will I get? You can see this, I will get a distribution something like this. So let's say, let's draw it. Well, anyways, draw it. Let's say I am predicting at this point, right? So let's say that is this point, right? My prediction will no longer be a point estimate. It will be something like, so my prediction is a PDF. My prediction will be a PDF. It is known as predictive distribution. So you do not predict a point estimate, you predict what is the PDF, given that your x in this case is input is 6. Okay. So even if your hyperparameter is same, and it will be same, you will be predicting a PDF, not a point. Okay. And from that PDF you can sample. Now I draw here a Gaussian because Gaussian process, your predictive distribution will be Gaussian. So because of that I drew Gaussian, but in other cases it may be non-Gaussian also. But for Gaussian process, your predictive distribution is Gaussian. Again, this is actually a conditional distribution. Okay. Clear? So now, let us try to understand. Okay. Some schematics taken from some lecture, which I will give you the. Someone else, although I made these figures today morning only, but it is inspired from some other lecture online. Okay. Actually, a stalwart of Gaussian process, Neil Lawrence. Okay. So what you are seeing at the top left, what is that equation? Standard normal Gaussian, right? Multivariate Gaussian, standard normal, mean 0. Actually not standard normal because sigma is not diagonal, but 0 mean bivariate Gaussian. Okay. And how does sigma look like? It's shown here, 1, 1 diagonally and 0.9, 0.9. How will the contour look like for this? What I have drawn is the contour of that. Why the contour looks like this? Because the correlation is positive and almost 1. Because the correlation is positive and almost 1, positive, that's why the positive slope, and almost 1, that's why it has shrinked. Okay, if it was negative, then you will see the opposite slope and it will still shrink, right? What do you expect will happen if I reduce 0.9 without changing the sign? Expand. This is 0.7. This is what you expect, right? If I make it even more, reduce it even more, it should expand even further. 0.4, 0.7, 0.4. Reduce it even further, 0.1. Almost a circle. At 0, it will be circle. This is how the contour of a Gaussian distribution looks like. I think I discussed with someone outside the lecture, someone was asking how the contour will look. This is how it looks, right? So this is a bivariate Gaussian, and the contour of bivariate Gaussian is a function of the correlation function, and the center of it is a function of the mean. You will see that the center is at 0 and 0, 0, 0, because the mean is 0. If I change the mean, the center will change. If I change the covariance, or in this case correlation, this will keep on changing or increasing, right? Clear? Now, as I was saying, what will happen if I condition it at a value? This is what will happen. So what you are seeing on the left is the same plot, 0.9, left one, right? What does conditioning means? Conditioning in x1 means you will keep the value of x1 fixed at a point, which means I have kept it fixed at this point, and I am looking at the distribution or the variability of the other variable, which is y, or y1 and y2, right? So how will y2 vary? Y2 will vary as per this contour, whatever you see here. Now if I go back to the 0.91, you can imagine that if I draw it here, right? So more samples will be here and less samples will be away from this, because the contour lines away are showing the low probability points. Same thing will happen here. You can see wherever there is a finite probability, which is the red line, there are samples. But here you will see no samples. There is no samples here, right? Correct? So this red that you are seeing on the left is the probability of y2 given y1 is equal to 1.5. Probability of y2 given y1 is equal to 1.5. How will probability of y1 given y2 look like? How will you get that? Horizontal line. Right? And this is Gaussian, by the way. You might think that the tail is longer because that's only because I have drawn it like that. It will go from infinite to infinite because for the multivariate it goes from minus infinite to plus infinite. The same thing I have drawn by rotating it on the right. Same thing. This is the same thing. This one only rotated. This red plot, it has been rotated and shown here. Okay. And it's a Gaussian distribution. The conditional distribution in Gaussian is this one. Okay. Now what will happen if you increase the covariance or reduce the covariance correlation? You know that this one was becoming flatter. Same thing will happen with the PDF. See, now these points are, red points are well spread. And because the red points are well spread, here it is flatter. Even more flatter. Standard Gaussian. Standard Gaussian because left one was multivariate standard Gaussian. Okay. Clear what is happening? So this is basically how the conditional distribution looks like if you plot it. Okay. Now, what is the problem with this visualization? Can you tell me? You cannot visualize beyond 2 dimensions. 2D becomes your limitation, right? So let me introduce a new visualization and then I'll stop for today, okay? Because I don't have time. I'll take 5 minutes and that will. So this is some Gaussian, right? And the red point you see, what is that? Some sample, one sample, right? And that sample will have a value. It will have a x comma y. What is x? The horizontal distance. What is y? The vertical distance. Right? So if I start from here, this is the sample. This is the x distance, x coordinate of that sample. This is the y coordinate of that sample. Right? Clear? Now let us introduce a new representation. We will represent it in something like this, where the x-axis represents the index of the variable. So what will be 1? 1 will be, in x-axis what will be 1? Let's say y1, the x, and 2 will be y2, 3 will be y3, 4 will be y4, and like that. Right now I have 2, so I'll only need 1 and 2. And then for y1, what is the value? 2.46 or something like that, right? 2.46. The horizontal distance is 2.46. So, you see this point? This point here? This is representing the 2.46 from this, obviously, from this point, right? X-axis. What will be this value? 1.58. So maybe somewhere here, right? You see, it is there. And then how will you represent the sample? By connecting these 2 points. So that sample is now represented by this line. That sample is now represented by this line, these 2 points connected, right? If you draw different samples, the line will change. Top left, the sample is at the top, so y is more, x is less. That you see in the pattern that the line is something like this. Top left, the line is something like this because y is more, x is less. The second one, y is less, x is more. another sample, it goes like this. And like that, you can get different samples, right? So, and different samples becomes in this new representation, different line segments. And that will move up and down. It cannot move right, left and right, but it will only move up and down while changing the angle. So, it has 2 degrees of freedom, if you think of it like that. Because x can go or y can go. So, 2 degrees of freedom. Or you can think that one will go and the angle will change. Again, then 2 degrees of freedom. Okay. The same business you can do with conditional as well. So, sorry, okay. Oh, the slides are not updated. Some of the slides did not get. So, I had the conditional one also, but it did not get updated. Anyways, I don't have time also. Yeah, I'm out of time. So, we'll start with this representation once more and do the conditional visualization of this. And from there, you can easily understand that this will soon become Gaussian process. In the infinite dimension, this x-axis will become large. And instead of this line, you will have line connected like this. And that is like a function, right? So, we'll go there next time. Okay. But this representation is very interesting. And we'll talk more about this representation next time. Okay. And this, but the point is that this allows you to generalize. That is the main point. Okay. Okay. Thank you.